Okay, welcome to a lesson about diagonal projectiles. With a diagonal projectile, what we're doing is we're throwing an object with both a little bit of horizontal, a little bit of vertical. This is the usual motion of most objects. It's really hard to throw something exactly horizontal. So we either tend to throw things upwards into the air, or we might even tend to throw them downwards into the air. So this diagonal projectile is actually the normal motion. In a diagonal projectile, we've got this right here. This initial velocity is the initial diagonal velocity. And because we're throwing it at a diagonal, then what we notice is that it has components. It has a vertical component, and it has a horizontal component. The vertical and horizontal can be labeled with adjacent and opposite. And the diagonal velocity then is the hypotenuse. So to get the vertical component, to get VIY, to get that opposite side, all we have to do then is to take the hypotenuse and multiply it by the sine of the angle that is at the x-axis. To get the adjacent side, which in this case is the horizontal, to get VIX, all we have to do is go v cos theta to get that initial x velocity. So what we found then is we have found the velocities at this initial point right here, right? So that's the initial point. And so we have found this VIY initial, and we found that VIX initial. Because there is zero acceleration, there is no forces acting in the horizontal if we ignore air resistance, then this initial velocity x is going to be the same throughout, right? Zero acceleration gives me constant velocity. So at every point along this path, Vix is what that horizontal velocity is. And because the acceleration is zero, then in this quadratic equation, what we see then is we see that the formula that governs this motion is just a uniform motion, constant velocity formula. VIY is, of course, being influenced by gravity, right? The initial vertical velocity is being influenced by a downwards gravitational acceleration. And obviously then that means this is going to slow down. So when we look at the vector, we should see that the vector in the vertical direction is getting smaller as it goes up. So this is the vertical velocity upwards at this point. At the top of the motion, there's an instantaneous velocity, which is 0. So Vy at this point is 0. And then after it reaches the top of the motion, we know that the velocity vertical is going downwards. And so then we know that this object will then speed up, and we should then get a longer vector happening. And so we see then that this velocity down here at this point is starting to increase until it gets down to this velocity y at the ground. So a couple of things about the vertical motion. It behaves like an object that's thrown vertically, right? So this motion of up and down is just that motion that we look at when we throw an object straight up into the air. The initial velocity is VIY in the vertical direction, and the acceleration, of course, 9.81 meters per second squared downwards. A couple of other notes: at any given height, the velocity up and the velocity down are the same. So if we look at this height right here, we notice that this velocity up and this velocity down must be equal at that height. So at any height. So when the object hits the ground again, then this y velocity right here is actually the final velocity, and that final velocity is actually equal to the initial velocity, but just in the opposite direction. And so these two things we can make of, or make use of, sorry, when we solve problems for these projectiles. Also, we know that for the same height, the time up is equal to the time down from that or to that particular height. So if I measure the time to go from the ground up to the top, And if I measure the time to go from the top down to the bottom, then the time up and the time down are equal. And this overall projectile path is a parabola. It's governed by a quadratic equation. And so quadratic equations produce parabolas, and so we get a parabolic path.